at each point in M a subspace of TPM. So if this is R3 like we said, okay, it's of course a manifold. This is R3, just bear with me here for a minute please. If this is R3, at each point in R3, at each point, this is a manifold, three-dimensional manifold. At each point of a manifold, we have something called tangent space, right? What's the tangent space? This is the set of all velocities at that point, okay? What's the tangent space of R3 at any point? Anybody can guess? What's the tangent space?
Q.
Say it again, please.
Q.
Q? Yeah, which is, again, it's R3, right? Because the tangent space is the set of all velocities. At this point, freely, I'm allowed to go in x, y, z velocity, right? Velocity-wise. So yeah, my tangent space is a three-dimensional space. And this is for any Rn, okay? R3, the tangent space of it is R3, okay. I'm here and I have my whole tangent space at this point, my whole tangent space at this point is R3, it's three-dimensional. I'm saying that the distribution is just a part of that. So maybe my distribution at this point gives me a plane, this horizontal plane, and maybe at this point gives me this vertical plane, maybe at that point gives me that plane, and so on and so on. So simply, the distribution is just giving you, at each point, part of the tangent space, okay? So in this language, actually the distribution simply can be span of some collection of vector fields, right? So if you give me maybe two vector fields, okay, at each point I'm gonna evaluate these two vector fields, they're gonna give me two velocity vectors. Well, the span of them will be the distribution. At this point, I have two velocity vectors here and there, so the span of them gives you the distribution. Okay? And so on and so on. Of course, it doesn't have to be two-dimensional out of three-dimensional, it's just anything. 1 out of 3, 2 out of 6, whatever. Given some manifold of any dimension, the tangent space has the same dimension, right, of the manifold, and then your distribution, depending on its type, just giving you part of it. So it's simply a collection of vector fields. Like here, I have two vector fields. So a collection of vector fields, okay? Any question about what we mean by distribution? Any collection? Any question? Sorry. It's a collection of vector fields. So some technicality, regular distribution means constant rank. So the rank of these vector fields, the rank of your collection at each point is the same. And this means that at each point, say if we're talking about this example, at each point you have two independent vectors. I cannot have two here, so my subspace is a plane, and then over there I just have one. The other one is simply zero or dependent now. So my distribution here will be just a line. It cannot be a line here, a plane here. No, just to make things consistent. If it's a plane, it has to be plane at all points. If it's a line, it has to be line at all points. This is what we mean by a regular distribution. Okay, that's constant rank. Okay, any question about that? Integrable distribution, as the name may tell. Anybody can suggest what do you mean by integrable distribution? If we can integrate it. So, like I said, distribution is just a collection of velocity vectors, right? Vector fields. Collection of velocity vectors. Integrable distribution meaning that this guy. We can have a surface. There exists a surface or submanifold N that is subspace of M such that delta at any point covers the tangent space of N for all points of N. It means that there exists a surface such that these guys, these vectors, are always tangent to that surface. Okay? And here is our language, how we write it. There exists a surface smaller than your surface, possibly, such that this collection are always tangent to that surface. So this collection, the delta, at any point, covers the whole tangent space of that surface, not the great surface, of course. Right? Any question? You guys seem lost, and you're not asking questions. You're not. I don't know.
Could you repeat the last statement that there is a surface possibly smaller than?
Yeah, it's like here we have two vectors, a collection of these two vectors. We call this a distribution. That's as simple as this. So the collection of x and y is a distribution, and we're asking, okay, is this distribution integrable? What do we mean here? Okay, we mean that does there exist a surface, smaller surface, a sphere like this embedded in R3, the big surface? Does there exist a surface such that these two guys are always tangent to the surface? Such that these two guys actually form the tangent space of that surface. Okay? So here's the thing. There exists surface sum of your original surface n such that this distribution, which is the collection of these guys, covers equals to the whole tangent space of that smaller surface. Okay? Last word. Involutive. It's fancy, it's very easy. Involutive distribution means that whenever you have two vector fields in the distribution, their Lie bracket should be also in the distribution. So for all x and y in delta, for all x and y in your collection of vector fields, if you compute the Lie bracket, it has to be also in the collection. Okay? In other words, you cannot compute Lie brackets between any two vector fields and get something new. If you get something new, then it means that you will not be able to integrate. You will not be able to have a surface embedded. Okay. And here is the theorem, which is very simple and very powerful at the same time. It's called the Frobenius theorem. Frobenius theorem. And very easy to memorize. It's 1911. A regular, every word has a meaning. Regular means, well, the distribution is just consistent all the way. It cannot be plane here and line over there. It has constant rank. Your collection of vectors, you guys should be experts on rank. You're taking 200A or the equivalent civil engineering, you know this very well. So the rank of your collection of vectors has to be constant all the way. Okay, this means regular. Actually, we'll not deal with anything other than regular distribution, so that's fine. Take this for granted for the moment. A regular, smooth. Your vectors should be smooth. Your vectors are in general functions of the coordinates, right? These functions has to be smooth. Here's what differentiating. A regular smooth distribution